The universe is a place of unimaginable extremes, where forces so powerful they can bend light, distort time, and swallow entire stars exist in the darkest corners of space. Picture this, an object so dense, so massive, that it creates a gravity so strong not even light can escape its grip. This isn't science fiction, it's the reality of black holes, just one of the many mind-bending phenomena we'll explore today. From the mysterious pull of supermassive black holes to the ripples in spacetime known as gravitational waves, the cosmos is filled with gravitational forces that defy our understanding. In this video, we'll uncover 50 astonishing facts about the universe's most extreme gravitational forces, each one revealing just how strange and awe-inspiring our universe truly is. Get ready to dive into the depths of space mystery, where the rules of physics are pushed to their limits and the cosmos reveals its most incredible secrets. Let's begin this journey into the unknown, where gravity reigns supreme and the universe never ceases to amaze. Now, let's venture into the heart of one of the universe's most extreme gravitational marvels, the event horizon. Imagine standing at the edge of a cosmic abyss, a point so powerful it marks the boundary of no return. This is the event horizon, the defining feature of a black hole. At this point, the gravitational pull becomes so intense that nothing, not even light, the fastest thing in the universe, can escape its grasp. Think of it as a one-way door. Once you cross it, there's no turning back. This is what makes the event horizon one of the most extreme phenomena in the cosmos. It's a place where the familiar rules of physics break down and the universe reveals its most mysterious nature. The event horizon isn't just a concept, it's a real boundary that separates the known from the unknowable, a testament to the sheer power of gravity in shaping the fabric of space and time. Now let's dive into one of the most fascinating and bizarre effects of extreme gravity: spaghettification. Picture this: as an object, like a star or even an astronaut, gets too close to a black hole, it begins to experience an incredibly intense gravitational pull. But here's the twist: that pull isn't the same everywhere. The side of the object closest to the black hole feels a much stronger force than the side farther away. This difference in gravity stretches the object out, turning it into a long, thin strand, much like a piece of spaghetti being pulled apart. This process isn't just dramatic, it's also a stark reminder of how extreme gravity can distort reality. Scientists call this tidal forces at work, where the black hole's immense gravity overcomes the object's own structural integrity. Spaghettification is more than just a whimsical term. It's a real phenomenon that showcases the sheer power of black holes to reshape matter in ways that defy our everyday experiences. It's a vivid example of how the universe's most extreme forces can stretch the limits of what we thought was possible. Now, shifting our focus to an even grander scale, let's explore the giants of the cosmos: supermassive black holes. These colossal entities aren't just larger than their stellar counterparts, they're millions, even billions of times more massive, found at the hearts of nearly every galaxy, including our own Milky Way. Supermassive black holes wield an unimaginable gravitational force that shapes the very fabric of their surroundings. Take Sagittarius, a star, for example, the supermassive black hole at the center of our galaxy. With a mass roughly 4 million times that of the Sun, it exerts a gravitational pull so strong that it keeps the entire galaxy in orbit around it. But it's not just their size that's astonishing. These black holes play a crucial role in the evolution of galaxies. Their immense gravity can trigger the formation of stars, influence the movement of entire star systems, and even power some of the brightest objects in the universe, like quasars. Despite their destructive reputation, supermassive black holes are also cosmic architects, shaping the universe on a scale that's both awe-inspiring and humbling. Their existence reminds us that even in the vastness of space, gravity remains the master force, dictating the dance of galaxies and the destiny of stars. Now venturing into another extreme of cosmic gravity, let's explore the astonishing world of neutron stars. These dense remnants of massive stars are like the universe's ultimate pressure cookers. When a star explodes in a supernova, its core collapses under immense gravitational force, compressing protons and electrons into neutrons. The result is a neutron star, an object so incredibly dense that a single sugar cube-sized piece of its material would weigh billions of tons on Earth. Imagine the weight of a mountain packed into something you could hold in your hand. This extreme density gives neutron stars a gravitational pull that's second only to black holes. In fact, their surface gravity is about 100 billion times stronger than Earth's. To put it into perspective, if you could somehow stand on the surface of a neutron star, you'd be flattened into a thin layer almost instantly. Neutron stars also spin at mind-boggling speeds, some completing hundreds of rotations every second. This combination of density, gravity, and speed makes them some of the most extreme objects in the universe. They're not just cosmic oddities, they're natural laboratories for studying the limits of physics under conditions we could never recreate here on Earth. Their existence challenges our understanding of matter and gravity, reminding us that the universe is far more bizarre and fascinating than we often imagine. Now shifting our gaze to another groundbreaking discovery, let's dive into the fascinating world of gravitational waves. These are ripples in the fabric of spacetime itself, created by some of the most violent and energetic events in the universe. Imagine throwing a pebble into a still pond. The ripples that spread out are similar to how gravitational waves behave, except instead of water, they travel through the very structure of space and time. These waves are often produced by cataclysmic events, such as the collision of two black holes or the merger of neutron stars. The energy released in these events is so immense that it warps spacetime, sending waves rippling outward at the speed of light. In 2015, humanity achieved an incredible milestone when scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the very first time. This discovery confirmed a prediction made by Albert Einstein over a century ago and opened up an entirely new way of observing the universe. Unlike light, which can be blocked or distorted, gravitational waves travel unimpeded, giving us a clear window into cosmic events that were previously invisible. This breakthrough has allowed us to study black holes, neutron stars, and other extreme phenomena in unprecedented detail, revolutionizing our understanding of the cosmos. Gravitational waves are not just a scientific curiosity, they're a powerful tool that transforms how we explore the universe's most extreme gravitational forces. Now turning to one of the most mind-bending effects of extreme gravity, let's explore the phenomenon of time dilation near black holes. According to Einstein's theory of relativity, intense gravitational fields can warp not just space but time itself. Imagine two astronauts. One stays far from a black hole while the other ventures close to its event horizon. For the astronaut near the black hole, time would appear to pass much slower compared to their distant counterpart. This isn't just science fiction, it's a direct consequence of gravity's ability to stretch spacetime. To put it simply, the stronger the gravitational pull, the more time slows down. This effect, known as gravitational time dilation, has been confirmed through experiments here on Earth. For instance, atomic clocks placed at higher altitudes where Earth's gravity is slightly weaker tick faster than those at sea level. Near a black hole, this effect becomes extreme. If you could watch someone falling toward a black hole, you'd see their movement slow to a crawl, eventually seeming to freeze as they approach the event horizon. From their perspective, however, time would feel normal, while the rest of the universe would appear to speed up. This startling asymmetry in the flow of time is one of the most profound predictions of Einstein's theory, and it highlights just how strange and powerful the universe's most extreme gravitational forces can be. Now shifting our focus to another fascinating gravitational phenomenon, let's delve into tidal forces. These forces arise when there's a significant difference in gravitational pull on opposite sides of an object. Picture the moon's effect on Earth. The side of our planet closest to the moon feels a stronger gravitational tug than the side farther away. This imbalance creates a stretching effect which we see most visibly in the ocean tides. But tidal forces aren't just limited to Earth and the moon. They can have much more dramatic consequences in extreme environments. For example, when an object like a star or planet ventures too close to a black hole, the gravitational pull on its near side becomes immensely stronger than on its far side. This disparity can stretch and distort the object, a process often called tidal disruption. In some cases, the object is completely torn apart, forming a stream of debris that spirals into the black hole. Even moons in our solar system, like Jupiter's moon Io, experience intense tidal forces that generate volcanic activity as their interiors are stretched and compressed by the planet's gravity. Tidal forces remind us just how powerful and far-reaching gravity's influence can be, shaping not just planets and stars but entire cosmic landscapes. Now shifting our gaze to one of the most luminous objects in the universe, let's explore the incredible power of quasars. These cosmic beacons are among the brightest phenomena we've ever observed, shining with the energy of trillions of stars. But what fuels such intense brilliance? At the heart of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter spirals into this black hole, it forms a swirling disk of gas and dust, heating up to extreme temperatures and releasing staggering amounts of energy in the form of light and radiation. This process transforms the black hole's immediate surroundings into a quasar, a powerhouse that can outshine entire galaxies. But quasars aren't just about raw brightness. Their immense gravity plays a crucial role in shaping their environments. The gravitational pull of the supermassive black hole at the center draws in vast amounts of matter, creating jets of particles that shoot out at nearly the speed of light. These jets can stretch for thousands of light years, influencing the formation and evolution of galaxies as they interact with surrounding gas and dust. Quasars also act as cosmic lighthouses, helping astronomers study the early universe. Because they're so bright, we can observe them from billions of light years away, providing a glimpse into the conditions that existed when galaxies were first forming. The discovery of quasars has revolutionized our understanding of the universe, revealing the profound impact of supermassive black holes and their gravity on the cosmos. These celestial giants remind us that even in the vastness of space, gravity's invisible hand continues to shape the universe in extraordinary ways. Now shifting our focus from the immense gravitational pull of quasars, let's explore a fascinating theoretical counterpart to black holes, white holes. Imagine a black hole's polar opposite, where instead of pulling everything in, matter and energy are violently expelled outward. White holes are hypothetical objects predicted by the equations of general relativity, but unlike black holes, they have never been observed in the universe. If black holes are cosmic vacuum cleaners, white holes would be cosmic fountains, spewing out light, particles, and energy with tremendous force. The idea of white holes stems from the same mathematical framework that describes black holes, suggesting that if a black hole's singularity could reverse its behavior, it might transform into a white hole. Some scientists theorize that white holes could be the other end of a black hole, connected by a theoretical passage known as a wormhole. While this remains speculative, the concept challenges our understanding of spacetime and the behavior of extreme gravitational forces. White holes also raise intriguing questions about the nature of the universe. Could they be the source of mysterious bursts of energy or even the origins of entire galaxies? Despite their theoretical appeal, white holes face significant challenges in the realm of physics. For one, they violate the second law of thermodynamics, which states that disorder in the universe always increases. If white holes exist, they would seem to reverse this process, creating order from chaos. This paradox makes them a tantalizing yet elusive subject of study. While we may never observe a white hole directly, their existence continues to inspire scientists to push the boundaries of our knowledge, reminding us that the universe is full of mysteries waiting to be unraveled. Now turning to another mesmerizing phenomenon in the cosmos, let's dive into the concept of gravitational lensing. Imagine a massive object in space, like a galaxy or a black hole, sitting between us and a distant star or galaxy. Due to its immense gravitational pull, this massive object bends the very fabric of spacetime around it. When light from the distant object travels through this warped spacetime, it doesn't move in a straight line as we would expect. Instead, it follows the curve created by the gravity of the massive object. This bending of light acts like a cosmic magnifying glass, distorting and amplifying the image of the distant object. One of the most striking effects of gravitational lensing is the creation of Einstein rings, named after Albert Einstein, who first predicted this phenomenon. These rings appear as perfectly circular arcs of light, formed when the distant object, the massive lensing object, and the observer are perfectly aligned. But gravitational lensing isn't just about creating beautiful visuals, it's a powerful tool for astronomers. By studying these distorted images, scientists can measure the mass of the lensing object, even if it's invisible like dark matter. It also allows us to see objects that are otherwise too far away or faint to observe directly. Gravitational lensing has revealed some of the most distant galaxies in the universe, giving us a glimpse into the early stages of cosmic history. This incredible interplay between gravity and light continues to deepen our understanding of the universe, showcasing how even the most extreme forces can reveal the hidden wonders of the cosmos. Now shifting our gaze to one of the most perplexing mysteries in the cosmos, we encounter the Great Attractor. Nestled in the vast expanse of space, this enigmatic region exerts an overwhelming gravitational pull, drawing entire galaxies toward it at astonishing speeds. Located around 250 million light-years away from Earth, the Great Attractor resides in the direction of the Centaurus constellation. Despite its immense influence, it remains shrouded in mystery because our view of it is obscured by the dense plane of our own Milky Way galaxy, known as the Zone of Avoidance. Scientists believe this gravitational anomaly could be a massive concentration of dark matter and galaxies, but its exact nature is still a subject of intense study. What makes the Great Attractor even more fascinating is its role in the large-scale structure of the universe. Along with the Shapley supercluster, it's part of a cosmic tug-of-war, pulling galaxies and galaxy clusters into its grasp while shaping the flow of matter on an unimaginable scale. This gravitational dance not only reveals the interconnectedness of the universe, but also highlights how even the most distant forces can shape the fate of galaxies, including our own. The Great Attractor reminds us that there are still profound secrets lurking in the cosmos, waiting to be uncovered by the next generation of explorers and scientists. Now shifting our focus to an invisible yet fundamental force shaping our universe, we delve into the role of dark matter. While it cannot be seen directly, dark matter makes up about 85% of all matter in the cosmos, exerting a gravitational influence that holds galaxies together and shapes their formation. Without it, stars and galaxies would fly apart due to the lack of sufficient visible matter to generate enough gravitational pull. Dark matter's presence is inferred through its effects, such as the way it bends light from distant objects, a phenomenon known as gravitational lensing. This invisible substance also plays a crucial role in the large-scale structure of the universe, forming a cosmic web that connects galaxies and galaxy clusters across vast distances. While the exact nature of dark matter remains one of astronomy's greatest mysteries, its gravitational effects are undeniable, reminding us that much of the universe's power lies hidden in the unseen. As we explore the vast mysteries of the universe's gravitational forces, let's turn our attention to a theory that paints a dramatic picture of its ultimate fate. The Big Crunch theory suggests that the universe's current expansion could one day reverse, collapsing everything back into a single point. This idea hinges on the power of gravity, which over time could overcome the outward push of dark energy, pulling galaxies, stars, and even space itself inward. Imagine the universe, instead of expanding endlessly, shrinking back to a state of unimaginable density, much like the beginning of the Big Bang. While this theory isn't the most widely accepted today, it raises fascinating questions about the balance between gravity and other cosmic forces and how they might shape the universe's destiny. It's a reminder that even the largest structures in the cosmos are bound by the eternal pull of gravity. Now shifting our gaze to a cosmic phenomenon that is as dazzling as it is destructive, let's explore the incredible world of kilinovae. These are colossal explosions that occur when two neutron stars, incredibly dense remnants of dead stars, collide with each other. The energy released in such an event is so immense that it outshines entire galaxies for a brief moment. But what makes kilinovae truly fascinating is their gravitational impact. When neutron stars merge, they create ripples in spacetime known as gravitational waves, which we've previously discussed. These waves carry information about the collision across the universe, providing scientists with a unique window into these extreme events. Additionally, the collision spews out heavy elements like gold and platinum, enriching the cosmos with materials essential for planets and even life. Kilinovae are not just spectacular fireworks, they are also cosmic forges, shaping the universe in ways we're only beginning to understand. Now shifting our focus to a critical boundary in the life cycle of stars, let's explore the Chandrasekhar limit. This limit, named after the brilliant astrophysicist Subrahmanyan Chandrasekhar, defines the maximum mass a white dwarf, the remnant of a star like our Sun, can have before it undergoes a dramatic transformation. The Chandrasekhar limit is approximately 1.4 times the mass of our Sun. If a white dwarf accumulates more mass than this, whether through pulling material from a companion star or other processes, it can no longer support itself against the crushing force of its own gravity. The result is a catastrophic collapse, leading to the formation of either a neutron star or, in some cases, a black hole. This limit is a cornerstone of astrophysics, helping us understand the fate of stars and the incredible forces at play in the universe. It's a reminder of how even the smallest changes in mass can trigger some of the most extreme cosmic events. Now exploring the heart of a black hole, we encounter one of the universe's most perplexing mysteries, gravitational singularities. These are points of infinite density where the laws of physics as we know them cease to function. At the center of every black hole lies a singularity, a region where matter is crushed to an infinitely small point and space-time becomes infinitely curved. This defies our understanding of nature, as it's impossible to comprehend infinite density or a point where gravity becomes infinitely strong. Scientists are baffled because singularities create a breakdown in Einstein's theory of general relativity, which cannot explain what happens at such extremes. To unravel this mystery, researchers are exploring theories like quantum gravity, which might bridge the gap between general relativity and quantum mechanics. Gravitational singularities remind us that even in a universe filled with wonders, there are still frontiers of knowledge that remain tantalizingly out of reach. Now shifting our focus to another fascinating gravitational phenomenon, let's explore the Roche limit. This is the critical distance at which a celestial body, like a moon or asteroid, gets torn apart by the overwhelming gravitational pull of a larger object, such as a planet or star. The Roche limit occurs because the side of the smaller object facing the larger one experiences a much stronger gravitational force than the opposite side. This difference in force, known as tidal force, stretches the smaller body until it can no longer hold itself together. For example, if a moon ventures too close to its planet, it could be shredded into rings or debris. Saturn's iconic rings are thought to be the result of moons or other objects that crossed the planet's Roche limit and were destroyed. Understanding this limit not only helps explain the formation of planetary rings, but also highlights the delicate balance of gravitational forces in our universe. As we continue to study these extreme interactions, we gain deeper insights into the dynamic and ever-changing nature of cosmic systems. Now turning to one of the most powerful events in the cosmos, let's dive into gamma-ray bursts. These are the most energetic explosions known to occur in the universe, releasing immense amounts of radiation in just a few seconds. Often linked to the collapse of massive stars or the collision of neutron stars, gamma-ray bursts are thought to involve extreme gravitational forces. When a massive star exhausts its fuel and collapses into a black hole, it can trigger a gamma-ray burst as jets of energy are ejected at nearly the speed of light. Similarly, when two neutron stars collide, their immense gravitational pull can create a burst of gamma rays along with gravitational waves. These events are so intense that they can outshine entire galaxies for a brief moment, even when observed from billions of light years away. By studying gamma-ray bursts, scientists gain valuable insights into the behavior of matter and gravity under the most extreme conditions. These bursts serve as cosmic laboratories, helping us understand the universe's most violent and fascinating phenomena. As we explore the vastness of the cosmos, let's turn our attention to the expansion of the universe. This phenomenon, first discovered by astronomer Edwin Hubble in the 1920s, reveals that galaxies are moving away from each other, stretching the fabric of space itself. Gravity plays a crucial role in this cosmic dance as it pulls matter together, slowing down the expansion. However, something mysterious is counteracting gravity's pull: dark energy. This unseen force is causing the universe to expand at an accelerating rate, pushing galaxies apart faster than gravity can hold them together. Scientists believe that dark energy makes up about 68% of the universe, while gravity, acting through visible and dark matter, accounts for the rest. This delicate balance between gravity and dark energy shapes the fate of the cosmos, determining whether it will expand forever, collapse back on itself, or reach a stable state. Understanding this interplay is one of the greatest challenges in modern astrophysics, offering clues to the universe's ultimate destiny. As we continue to study these forces, we uncover more about the intricate mechanisms that govern everything from the smallest particles to the largest structures in existence. Now turning to a fascinating and lesser-known phenomenon, let's explore the concept of micro-black holes. These tiny yet incredibly dense objects are theorized to exist in the universe, packing the gravitational might of a black hole into a size much smaller than even an atom. Unlike their supermassive counterparts, micro-black holes are thought to form under extreme conditions, potentially created in the earliest moments of the universe or through high-energy collisions in particle accelerators. Scientists hypothesize that they could have masses ranging from a few micrograms to thousands of tons, yet their gravitational pull would remain incredibly intense. One of the most intriguing aspects of micro-black holes is their potential to evaporate over time, a process predicted by physicist Stephen Hawking, where they emit radiation and lose mass until they eventually vanish. While no micro-black holes have been directly observed yet, their existence could provide valuable insights into the nature of gravity, quantum mechanics, and the conditions of the early universe. As we continue to probe the cosmos, these elusive objects remain a tantalizing mystery, inviting us to rethink our understanding of the universe's most extreme forces. With this in mind, let's move forward to uncover even more mind-bending facts about the cosmos. Now shifting our focus to one of the most thought-provoking theories in modern physics, let's delve into the holographic principle. This groundbreaking idea suggests that all the information contained within a black hole is not lost forever but is instead encoded on its surface, much like a hologram. In simple terms, a hologram is a two-dimensional surface that can project a three-dimensional image. Similarly, the holographic principle proposes that the entire complexity of a black hole, including everything that falls into it, can be represented by data stored on its event horizon, the boundary beyond which nothing can escape. This theory challenges our traditional understanding of space and dimensions, implying that the universe itself might operate like a cosmic hologram, where the information about three-dimensional objects is encoded on a two-dimensional surface. Initially proposed in the context of black holes, the holographic principle has since expanded to offer a radical new perspective on the nature of reality itself, suggesting that our three-dimensional universe might be a projection of data stored on a distant two-dimensional boundary. While this concept remains theoretical, it has profound implications for our understanding of gravity, quantum mechanics, and the very fabric of spacetime. As we continue to explore the universe's most extreme forces, the holographic principle invites us to reconsider the very nature of existence, blurring the lines between science and philosophy. With this mind-expanding idea in place, let's journey further into the cosmos to uncover even more astonishing facts. Now exploring another fascinating concept in the realm of extreme gravitational forces, let's turn our attention to wormholes. These hypothetical passages, often depicted in science fiction, are theorized to act as shortcuts through the fabric of spacetime, potentially connecting two distant points in the universe. Imagine folding a piece of paper so that two far-apart dots touch. A wormhole would be the tunnel that bridges them. In scientific terms, a wormhole is a solution to the equations of general relativity, suggesting that spacetime can be warped to create a tunnel-like structure. However, wormholes are not just simple tunnels. They are incredibly unstable and would require exotic matter with negative energy to remain open and traversable. While no wormhole has ever been observed, their existence could revolutionize our understanding of the universe, offering the possibility of interstellar travel or even time travel. The concept of wormholes also raises profound questions about the nature of spacetime and whether such shortcuts could exist naturally or be created artificially. As we continue to probe the mysteries of the cosmos, wormholes remain a tantalizing idea, blending the boundaries of science and imagination. With this intriguing concept in mind, let's journey further into the universe to uncover even more astonishing gravitational phenomena. Now shifting our gaze to one of the universe's most puzzling regions, we encounter the Boots Void. This vast expanse, often referred to as the Great Nothing, spans an astonishing distance of around 330 million light-years across, making it one of the largest known voids in the observable universe. Unlike the densely packed regions of space filled with galaxies, the Boots Void is eerily sparse, containing only a handful of galaxies compared to the thousands expected in a region of its size. This scarcity of matter creates a unique gravitational environment, where the forces we typically associate with galaxies and clusters are largely absent. Scientists believe that the void's gravitational properties might provide clues about the large-scale structure of the universe and the influence of dark energy. Despite its emptiness, the Boots Void remains a source of fascination, challenging our understanding of how matter is distributed across the cosmos. As we delve deeper into the mysteries of this enigmatic region, we're reminded that even the emptiest corners of the universe hold profound secrets waiting to be uncovered. With this intriguing anomaly in mind, let's continue our journey through the universe's most extreme gravitational forces. Now exploring another cosmic mystery, we turn our attention to the Fermi paradox and its intriguing relationship with extreme gravitational forces. The Fermi paradox poses a simple yet profound question. If the universe is so vast and filled with countless stars and planets, why haven't we detected any signs of extraterrestrial life? One possible explanation lies in the role of gravity, particularly in its most extreme forms. For instance, regions dominated by intense gravitational forces, such as those near black holes or neutron stars, could be lethal to any form of life, making these areas uninhabitable. Additionally, the gravitational pull of supermassive black holes at the centers of galaxies might disrupt the formation of stable planetary systems, limiting the potential for life to thrive. On a larger scale, the gravitational influence of dark matter and dark energy could shape the distribution of galaxies in ways that isolate civilizations from one another, making interstellar communication or travel nearly impossible. While these ideas are speculative, they highlight how gravity, in its most extreme manifestations, could be a key factor in explaining the apparent silence of the cosmos. As we ponder this paradox, we're reminded that the universe's most powerful forces might hold the answers to some of its greatest questions. With this thought in mind, let's continue unraveling the mysteries of gravity's role in shaping the cosmos. Moving forward, we encounter a fascinating mystery from our own solar system, the Pioneer anomaly. In the late 20th century, scientists observed something strange happening with the Pioneer 10 and Pioneer 11 spacecraft. As these probes traveled farther away from the Sun, they began to slow down more than expected, experiencing a tiny but consistent acceleration toward the Sun that couldn't be explained by known forces like gravity or solar radiation. This unexplained phenomenon became known as the Pioneer anomaly and puzzled researchers for decades. Some speculated that it could be due to unknown gravitational effects, perhaps from dark matter or even subtle deviations in our understanding of gravity itself. Others considered more practical explanations, such as heat radiating unevenly from the spacecraft's power systems, while later studies suggested that thermal radiation was likely the primary cause. The Pioneer anomaly remains an important reminder of how much we still have to learn about the forces shaping our universe. It also highlights the ongoing need for precise measurements and open-minded exploration as we seek to unravel the cosmos' deepest secrets. With this intriguing case in mind, let's continue our journey into the mysteries of gravity. Now shifting our gaze beyond the familiar planets, let's explore the Kuiper Belt, a vast, icy frontier at the edge of our solar system. This region, stretching far beyond the orbit of Neptune, is home to countless icy bodies, including dwarf planets like Pluto and Eris. The Kuiper Belt's gravitational influence plays a crucial role in shaping the dynamics of our solar system. Its collective mass, though spread across a vast area, exerts a subtle but significant pull on the orbits of objects within and beyond it. Scientists believe the Kuiper Belt acts as a gravitational buffer, helping to stabilize the outer solar system by influencing the trajectories of comets and other small bodies. Some of these objects are even nudged inward, becoming the short-period comets we occasionally see streaking across our skies. The study of the Kuiper Belt also provides clues about the early solar system, as its icy remnants are thought to be frozen relics from the time of planetary formation. By understanding the gravitational forces at work here, we gain deeper insights into how our cosmic neighborhood came to be and how it continues to evolve. Now venturing even further into the depths of our cosmic neighborhood, we encounter the Oort cloud, a mysterious and distant shell of icy objects that surrounds our solar system. Named after the Dutch astronomer Jan Oort, this vast region is believed to be the source of long-period comets that occasionally visit the inner solar system. Unlike the Kuiper Belt, which lies just beyond Neptune, the Oort cloud extends much farther, stretching nearly halfway to the nearest star. The gravity of the Sun, though significantly weaker at this immense distance, still holds sway over these icy bodies, keeping them loosely bound to our solar system. The Oort cloud is thought to contain trillions of objects, ranging from small icy chunks to larger bodies, all remnants of the solar system's formation billions of years ago. As these objects are perturbed by the gravitational influence of passing stars or the galaxy itself, some are sent hurtling toward the sun, becoming the spectacular comets that light up our night skies. Studying the Oort cloud not only helps us understand the outer limits of the sun's gravitational reach, but also provides a glimpse into the earliest days of our cosmic home. Now delving into the heart of our own galaxy, we arrive at the Milky Way's galactic core, a region of unimaginable gravitational intensity. This central hub is dominated by Sagittarius, a star, a supermassive black hole with a mass over 4 million times that of our Sun. The gravitational forces here are so extreme that they warp the very fabric of spacetime, bending the paths of nearby stars and gas clouds into chaotic orbits. These stellar objects whirl around the black hole at astonishing speeds, some traveling at millions of miles per hour as they are pulled by its immense gravity. The area surrounding Sagittarius, a star, is also a hotbed of cosmic activity, with vast streams of gas and dust being drawn inward, heating up to incredible temperatures and emitting intense radiation before disappearing beyond the event horizon. This gravitational powerhouse not only shapes the structure of our galaxy, but also offers scientists a unique laboratory to study the behavior of matter under the most extreme conditions. Understanding the dynamics of the Milky Way's core helps us unravel the mysteries of how galaxies form, evolve, and interact across the cosmos, reminding us of the awe-inspiring forces that govern the universe. Now, shifting our gaze to the future of our cosmic neighborhood, we encounter a phenomenon of monumental scale, the impending collision between the Milky Way and Andromeda galaxies. Gravity, the same force that binds stars within galaxies, will orchestrate this grand cosmic event in about 4 billion years. Andromeda, our closest galactic neighbor, is currently hurtling toward the Milky Way at a staggering speed of roughly 250,000 miles per hour. As these two massive galaxies draw closer, their mutual gravitational pull will cause them to begin a slow, intricate dance, eventually merging into a single, larger galaxy. During this process, individual stars are unlikely to collide due to the vast distances between them, but the immense gravitational forces will dramatically reshape both galaxies, twisting their spiral arms and triggering bursts of new star formation. Over time, the chaos will settle, and the merged galaxy, often referred to as Milkomda, will emerge as a new galactic entity. This cosmic collision serves as a powerful reminder of gravity's role in shaping the universe on the grandest scales, offering us a glimpse into the dynamic and ever-changing nature of the cosmos. Now turning to the grand scale of the cosmos, we explore the Virgo supercluster, an immense gathering of galaxies that stretches across the universe. This supercluster, which includes our own Milky Way and the Andromeda galaxy, is one of the largest structures in the observable universe, containing thousands of galaxies bound together by gravity. At its heart lies the Virgo cluster, a dense group of galaxies that exerts a powerful gravitational pull on its neighbors. The gravitational forces within the Virgo supercluster are so strong that they influence the motion of galaxies over vast distances, shaping their paths and interactions. These forces also play a crucial role in the large-scale structure of the universe, as galaxies are pulled into filaments and clusters, forming a cosmic web of matter. The Virgo supercluster serves as a testament to gravity's ability to organize and govern the cosmos on an unimaginable scale, reminding us of the interconnected nature of all things in the universe. Now shifting our focus to the tiniest scales of the universe, we encounter the Planck length, a fundamental unit of measurement that represents the smallest possible distance in the fabric of spacetime. Named after physicist Max Planck, this length is approximately 1.6 times 10 to the power of -35 meters, a scale so unimaginably small that it's beyond the limits of our current technology to probe. The Planck length is not just a curiosity, it's deeply tied to the nature of quantum gravity, At this scale, the effects of gravity and quantum mechanics are thought to merge, creating a realm where the smooth fabric of spacetime breaks down into a foamy, chaotic structure. Scientists believe that understanding this scale could unlock the mysteries of quantum gravity, a theory that aims to unify Einstein's general relativity with the principles of quantum mechanics. While the Planck length remains a theoretical concept for now, it serves as a reminder that even the smallest scales of the universe hold profound secrets, challenging our understanding of space, time, and gravity itself. Now shifting our gaze to the earliest moments of the universe, we encounter the cosmic microwave background, a faint glow of radiation that fills the cosmos. This ancient light, often called the afterglow of the Big Bang, holds clues to the universe's infancy. Gravity played a crucial role in shaping this cosmic fingerprint. In the first moments after the Big Bang, tiny fluctuations in density caused regions of slightly stronger gravity to pull matter together. Over time, these gravitational seeds grew into the vast structures we see today, from galaxies to galaxy clusters. The cosmic microwave background captures these early fluctuations, showing us where matter began to clump together under gravity's influence. These imprints, though subtle, are like a cosmic blueprint, revealing how gravity sculpted the universe on the largest scales. By studying this background radiation, scientists can trace the story of gravity's impact from the universe's birth to the present day, offering a window into the forces that shaped everything we see around us. Now exploring the boundaries of our understanding, we venture into the intriguing concept of the multiverse theory. This idea suggests that our universe might be just one of countless others, each with its own unique set of physical laws. Gravity, the force we know so well, could behave entirely differently in these other universes. In some, it might be stronger, pulling matter together with such intensity that stars and galaxies form in ways we can hardly imagine. In others, it could be weaker, allowing matter to spread out thinly, creating vast, almost empty expanses. These variations in gravity could lead to universes where life as we know it is impossible, or where entirely new forms of existence thrive. The multiverse theory challenges us to think beyond the limits of our own universe, raising questions about the nature of reality itself. While this concept remains speculative, it opens up fascinating possibilities for how gravity shapes the cosmos on an unimaginable scale. As we ponder these ideas, we're reminded of how much there is still to discover about the forces that govern existence. Next, we'll consider the no-hair theorem, which simplifies the complex nature of black holes into just 3 defining properties. Now delving deeper into the mysteries of black holes, we encounter the no-hair theorem, a fascinating concept that simplifies these cosmic enigmas. This theorem suggests that black holes, despite their complexity, can be entirely described by just 3 fundamental properties: mass, charge, and spin. Imagine a black hole as a cosmic fingerprint. No matter how intricate it may seem, these 3 traits define its identity. The mass determines the black hole's gravitational pull, the charge reflects its electromagnetic influence, and the spin describes how it rotates through space. Everything else, from the material that fell into it to the history of its formation, is effectively erased, leaving behind a seemingly hairless object. This idea challenges our understanding of information and complexity in the universe, raising questions about what happens to matter and energy once they cross the event horizon. While the no-hair theorem provides a streamlined way to describe black holes, it also leaves us pondering the deeper mysteries of how these objects truly operate. Next, we'll explore the Eddington limit, which reveals the delicate balance between gravity and radiation in the life of a star. Now turning to the Eddington limit, we uncover a critical point in the life of a star where the forces of nature reach a delicate equilibrium. The Eddington limit represents the maximum brightness a star can achieve before the outward pressure of its radiation becomes strong enough to overcome the inward pull of its gravity. Imagine a star as a cosmic tug-of-war on one side, gravity relentlessly pulls matter inward, compressing it to sustain nuclear fusion at the core. On the other side, the intense radiation produced by this fusion pushes outward, trying to escape and disperse the star's material. When a star reaches the Eddington limit, this outward radiation pressure becomes so powerful that it begins to counteract gravity, potentially causing the star to lose its outer layers or even disrupt its stability. This limit is particularly significant for massive stars, as their immense energy output can push them close to or beyond this threshold. The Eddington limit not only shapes the behavior of individual stars, but also influences the evolution of galaxies, as it determines how much energy stars can release into their surroundings. Understanding this balance between gravity and radiation helps us grasp why some stars shine brighter than others and why they eventually meet their fate in spectacular ways. As we continue, we'll explore how gravitational forces intersect with the conditions for life in the universe. Now shifting our gaze to the Drake equation, we explore how gravity subtly shapes the possibilities for life in the universe. The Drake equation, a framework for estimating the number of intelligent civilizations in our galaxy, considers factors like star formation rates, planetary systems, and the likelihood of life-sustaining conditions. One often overlooked element in this equation is the role of gravity. For a planet to support life, it must orbit within a star's habitable zone where temperatures allow liquid water to exist. Gravity plays a crucial role here, determining the stability of orbits and the strength of a planet's atmosphere. Too much gravity and a planet's atmosphere might become too dense, trapping excessive heat. Too little and the atmosphere could dissipate, leaving the planet barren. Additionally, gravity influences the formation of planetary systems. Stars with strong gravitational fields can disrupt the accretion of planets, while those with weaker fields may allow for calmer conditions conducive to planet formation. Even the gravitational interactions between planets and moons can create tidal forces, potentially driving geological activity or maintaining liquid oceans, key ingredients for life. By integrating gravity into our understanding of the Drake equation, we gain a deeper appreciation for the delicate balance required to create and sustain life in the cosmos. As we move forward, we'll examine how gravitational forces continue to shape the universe's most profound mysteries. Now stepping into the realm of cosmic expansion, let's uncover the role of gravity in shaping the universe's growth as measured by the Hubble constant. The Hubble constant is a key number in astronomy, representing the rate at which the universe is expanding. It was first calculated by Edwin Hubble in the 1920s, who observed that galaxies are moving away from us at speeds proportional to their distance. But here's where gravity comes into play. While the universe is expanding, gravity acts as a counterforce, pulling matter together and slowing down this expansion. In regions of the universe where matter is densely packed, like galaxy clusters, gravity's pull is stronger, creating a tug-of-war with the outward push of expansion. This delicate balance between gravity and expansion is what determines the ultimate fate of the cosmos. If gravity were stronger, it could eventually halt and reverse the expansion, leading to a big crunch. If it were weaker, the universe might continue expanding indefinitely. The Hubble constant helps us measure this expansion rate, providing clues about the universe's past, present, and future. It's a testament to how gravity, though an invisible force, plays a pivotal role in the grand story of the cosmos. As we continue, we'll explore how this interplay between gravity and expansion leads to even more fascinating mysteries in the universe. Now diving deeper into the universe's intricate structure, let's explore the cosmic web, a sprawling network that connects galaxies across the cosmos. Imagine the universe not as a random scattering of stars and galaxies, but as an organized, interconnected system, much like a giant spider's web. This cosmic web is made up of filaments, or long strands of dark matter and gas that stretch across vast distances. These filaments act as the scaffolding of the universe, with galaxies and galaxy clusters forming at the points where they intersect. Gravity is the force that binds this entire structure together. It pulls matter into these filaments, creating dense regions where galaxies can form and evolve. But the cosmic web isn't just a static network. It's dynamic, constantly growing and shifting as gravity influences the movement of matter over billions of years. What's truly fascinating is that this web-like structure isn't something we can see directly. Instead, scientists map it by observing the distribution of galaxies and measuring the gravitational effects of dark matter. The cosmic web gives us a glimpse into the large-scale architecture of the universe, revealing how gravity shapes everything from the smallest galaxies to the largest superclusters. As we continue our journey, this interconnected web will lead us to even more astonishing discoveries about the forces that govern our cosmos. Now turning to the fascinating intersection of black holes and thermodynamics, let's explore the Bekenstein-Hawking entropy, a groundbreaking concept that bridges these two seemingly unrelated fields. Black holes, often thought of as inescapable voids, actually have a surprising connection to heat and disorder thanks to this theory, proposed by Jacob Bekenstein and later refined by Stephen Hawking. The Bekenstein-Hawking entropy suggests that black holes possess entropy, a measure of disorder or randomness. This was a radical idea because at first glance, black holes appear to be the ultimate destroyers of information, swallowing everything in their path. But Bekenstein and Hawking showed that black holes have a quantifiable amount of entropy, which increases with their surface area. What's remarkable is that this entropy isn't tied to the material that falls into the black hole, but rather to the black hole itself. Think of it like this: even though a black hole's interior might seem chaotic and unknowable, its surface area holds a hidden order encoded with information about its entropy. This discovery led to a deeper understanding of how black holes interact with the universe, revealing that they aren't just cosmic vacuum cleaners, but instead play a role in the grand thermodynamic dance of the cosmos. The Bekenstein-Hawking entropy remains a cornerstone of modern physics, challenging our perceptions of black holes and opening new doors to understanding the universe's most mysterious objects. Shifting our gaze to the realm of theoretical physics, let's dive into the intriguing concept of the Alcubierre drive, a concept that could revolutionize space travel as we know it. Proposed by physicist Miguel Alcubierre in 1994, this theoretical model suggests a way to achieve faster-than-light travel without breaking the laws of physics. The idea centers around manipulating spacetime itself, creating a warp bubble that contracts space in front of a spacecraft while expanding it behind. Essentially, the ship wouldn't be moving through space at incredible speeds. Instead, space itself would move around it. This would allow the craft to bypass the speed of light limit set by Einstein's theory of relativity. But how does gravity fit into this picture? The Alcubierre drive relies on extreme gravitational forces to warp spacetime, requiring the presence of exotic matter with negative energy density to create the necessary conditions. While this remains purely theoretical and faces significant challenges, such as the unknown properties of exotic matter and the immense energy requirements, the concept has captured the imagination of scientists and science fiction enthusiasts alike. It represents a bold step toward exploring distant stars and galaxies, offering a glimpse into a future where humanity might traverse the cosmos in ways we once thought impossible. The Alcubierre drive reminds us that even the most far-fetched ideas can inspire breakthroughs, pushing the boundaries of what we understand about gravity and the universe. As we venture further into the mysteries of the cosmos, let's turn our attention to the enigmatic CMB cold spot. This peculiar region, observed in the cosmic microwave background radiation, stands out due to its unusually low temperature compared to its surroundings. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The CMB cold spot, discovered in 2004, spans a vast area in the constellation Eridanus and has puzzled scientists ever since. Its temperature is significantly cooler than expected, sparking debates about its origin. One leading theory suggests that the cold spot could be the result of extreme gravitational forces. Massive structures, such as supervoid regions of space with far fewer galaxies, might stretch spacetime, causing light passing through to lose energy and appear colder. Another, more speculative, explanation involves the influence of a parallel universe or exotic gravitational effects beyond our current understanding. While these ideas remain unproven, the CMB cold spot serves as a reminder of how much we still have to learn about gravity and its role in shaping the universe. This cold patch in the sky continues to challenge our models, inspiring new research and theories that push the boundaries of cosmology. Now shifting our focus to a thought-provoking concept, let's explore the anthropic principle and its connection to gravity's fine-tuning in the universe. The anthropic principle suggests that the conditions of the universe must allow for the existence of observers like us. In other words, the fundamental constants of nature, including the force of gravity, appear to be precisely calibrated to make life possible. If gravity were even slightly weaker, matter would never clump together to form stars and galaxies. If it were slightly stronger, the universe would have collapsed back on itself long before life could emerge. This delicate balance has led scientists to wonder whether gravity's fine-tuning is simply a fortunate coincidence or if it points to something deeper. Some theorists propose that our universe is just one among many in a vast multiverse, each with different physical laws. In this scenario, we find ourselves in a universe where gravity happens to be just right for life because in others it isn't. Others argue that this fine-tuning might hint at an underlying design or natural principle we have yet to understand. While the anthropic principle doesn't provide a definitive answer, it invites us to ponder why the universe is the way it is and how gravity's precise strength plays a crucial role in our existence. This principle bridges the gap between cosmology and philosophy, reminding us that the forces shaping the cosmos are not just scientific phenomena, but also deeply tied to the question of why we are here. Now, let's turn our attention to a fascinating feature of our own galaxy, the Fermi bubbles. These colossal structures, stretching tens of thousands of light-years above and below the Milky Way's galactic plane, were discovered in 2010 by the Fermi Gamma-Ray Space Telescope. These immense bubbles emit high-energy gamma rays and are thought to be the remnants of a massive energy release from the supermassive black hole at the center of our galaxy, Sagittarius, a star. The origins of the Fermi bubbles are still a subject of intense study, but one leading theory suggests they were formed by a colossal outburst of energy, possibly triggered by the black hole devouring an enormous amount of matter millions of years ago. This event would have sent shockwaves and jets of high-energy particles shooting outward, creating the bubble-like structures we observe today. The gravity of the supermassive black hole played a crucial role in this process, as its immense pull likely directed the energy and matter into these distinct formations. The Fermi bubbles serve as a powerful reminder of how gravitational forces, even on a galactic scale, shape the universe around us, leaving behind awe-inspiring structures that continue to puzzle and intrigue astronomers. Now shifting our gaze to one of the most intriguing theories in astrophysics, let's explore the cosmic censorship hypothesis. This concept, first proposed by physicist Roger Penrose, suggests that singularities, those infinitely dense points at the center of black holes, are always concealed behind event horizons. In simpler terms, it means that no singularity can ever be naked or exposed to the rest of the universe. The event horizon acts as a cosmic veil, preventing the intense gravitational forces and infinite density of singularities from directly interacting with the outside world. This hypothesis is important because it helps preserve the predictability of our universe. Without the shielding effect of event horizons, the extreme conditions of a singularity could disrupt the very fabric of spacetime, leading to chaos in the laws of physics as we know them. While the cosmic censorship hypothesis remains unproven, it continues to spark debate and inspire research as scientists seek to understand the true nature of these enigmatic cosmic phenomena. It's a fascinating reminder of how gravity not only shapes the universe but also sets the boundaries that keep its most extreme secrets hidden from view. Now shifting our attention to another cosmic mystery, let's delve into the enigmatic phenomenon known as the dark flow. This peculiar gravitational force was first observed in 2008 when astronomers noticed that clusters of galaxies were moving in a specific direction at astonishing speeds, faster than the expansion of the universe itself. Unlike the predictable motion caused by dark energy or the gravitational pull of nearby structures, the dark flow suggests the presence of an unseen, immense gravitational force beyond the observable universe. Scientists believe this could be evidence of massive structures, possibly other universes, exerting their influence on our own. The dark flow challenges our understanding of the cosmos, raising questions about what lies beyond the limits of our observable universe. While its true nature remains shrouded in mystery, it's a captivating reminder that even the most extreme gravitational forces continue to unveil new secrets, pushing the boundaries of our cosmic knowledge. Now exploring another fascinating frontier, we dive into the perplexing realm of the quantum gravity paradox. At the core of this challenge lies the struggle to reconcile two of the most successful theories in physics: quantum mechanics and general relativity. Quantum mechanics brilliantly explains the behavior of particles at the smallest scales, while general relativity provides a robust framework for understanding gravity on cosmic scales. However, when we try to apply both theories to extreme conditions like those inside a black hole or the moment of the Big Bang, they seem to clash dramatically. For instance, general relativity describes gravity as the curvature of spacetime, while quantum mechanics suggests that forces are carried by particles. This incompatibility has left scientists grappling with questions like, how can gravity be both a force and a property of spacetime? And what happens to gravity at the smallest scales where quantum effects dominate? Efforts to unify these theories have given rise to ideas like string theory and loop quantum gravity, but a definitive solution remains elusive. The quantum gravity paradox not only challenges our understanding of the universe, but also drives the search for a deeper, more unified theory that can explain the cosmos in all its complexity. It's a reminder that even our most advanced scientific ideas are still works in progress, pushing us to rethink the very fabric of reality. Now shifting our focus to another cosmic puzzle, let's explore the galaxy rotation problem. When astronomers first studied the motion of galaxies, they expected stars on the outer edges to rotate more slowly than those near the center, much like planets in our solar system. However, observations revealed something astonishing. Stars in the outer regions of galaxies were moving far faster than predicted. This discrepancy between expectation and observation became known as the galaxy rotation problem. To explain this, scientists proposed the existence of dark matter, an invisible substance that doesn't emit light but exerts a gravitational pull. Dark matter is thought to form a vast halo around galaxies, providing the extra gravitational force needed to account for the faster rotation. Without dark matter, galaxies would simply fly apart due to their own speed. This discovery has profound implications, as it suggests that the visible universe, stars, planets, and gas, makes up only a small fraction of the total matter in existence. The galaxy rotation problem not only deepened our understanding of gravity, but also opened the door to one of the most tantalizing mysteries in modern astrophysics, the true nature of dark matter and its role in shaping the cosmos. Now, venturing into one of the most dramatic theories about the universe's future, we come to the Big Rip. Imagine a scenario where dark energy, the mysterious force driving the universe's accelerating expansion, becomes so powerful that it completely overcomes gravity. This isn't just a gentle drift of galaxies away from each other. It's a catastrophic event where dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even the very fabric of spacetime itself. In this scenario, the universe doesn't just end in a cold, distant fade, but in a violent, explosive finale. The Big Rip suggests that everything we know, from the largest galaxy clusters to the smallest atomic particles, could be ripped apart in an instant, leaving behind a universe of isolated fragments. While this theory is still speculative, it challenges our understanding of gravity and forces us to confront the possibility that the universe's ultimate fate might be far more extreme than we ever imagined. It's a stark reminder of the delicate balance between gravity and dark energy, a balance that, if disrupted, could lead to an unimaginable cosmic catastrophe. Now shifting our focus to one of the most profound mysteries in astrophysics, we encounter the paradox of infinite gravity. At the heart of every black hole lies a singularity, a point where gravitational forces become infinitely strong and our current laws of physics break down. This paradox arises because, according to Einstein's theory of general relativity, the immense gravitational pull compresses matter into an infinitely small point of infinite density. But here's the catch: infinities are not just mathematically challenging, they are also physically impossible in the real world. This contradiction forces scientists to confront the limitations of our understanding. What happens at the center of a black hole? Does gravity truly become infinite, or do we need a new framework like quantum gravity to explain this phenomenon? The paradox of infinite gravity pushes the boundaries of our knowledge, reminding us that even the universe's most extreme forces are still shrouded in mystery. It's a humbling thought that challenges us to rethink the very foundations of physics. Now, looking ahead to the horizon of scientific discovery, we turn our attention to the future of gravitational research. One of the most exciting developments on this front is the Laser Interferometer Space Antenna, or LISA, a groundbreaking mission set to launch in the coming years. Unlike Earth-based detectors, LISA will operate in space, forming a triangle of 3 satellites millions of miles apart. This setup will allow it to detect gravitational waves with unprecedented precision, opening a new window into the universe's most extreme events, like the collisions of supermassive black holes and the birth of cosmic structures. Beyond LISA, advancements in quantum sensors and next-generation telescopes promise to deepen our understanding of gravity's role in shaping the cosmos. These technologies could help us test theories of quantum gravity, explore the nature of dark matter, and even uncover hidden dimensions of space and time. As we stand on the brink of these discoveries, the future of gravitational research holds the potential to revolutionize our understanding of the universe, revealing secrets that have eluded us for centuries. It's a thrilling reminder that the quest to unravel the mysteries of gravity is far from over, and the best may yet be to come. Now, as we reach the final stretch of our cosmic journey, let's take a moment to reflect on the awe-inspiring discoveries we've uncovered. From the immense pull of black holes and the stretching forces of spaghettification to the mysterious Great Attractor and the ripples of gravitational waves, the universe's extreme gravitational forces continue to captivate and challenge our understanding. These 50 facts have shown us just how powerful and intricate gravity is, shaping everything from the smallest particles to the largest structures in the cosmos. Whether it's the mind-bending concept of time dilation near black holes or the gravitational lensing that bends light across vast distances, each revelation reminds us of the universe's endless wonders. As we stand on the brink of new discoveries with missions like LISA and advancements in quantum gravity, the future promises even more insights into these cosmic mysteries. If you've enjoyed this exploration, don't forget to hit the like button, share your thoughts in the comments, and subscribe for more deep dives into the mysteries of space. Together, let's keep unraveling the secrets of the universe, one gravitational force at a time. Until next time, keep looking